We're moving on to another method of statistical inference, the confidence interval. This video will define the term and give a calculation approach by simulation, much like we did for the p-value for hypothesis testing. To compare, let me review what we defined for hypothesis testing. An hypothesis is a statement that something is going on with the statistic, something other than a null hypothesis. The example we did in the last video had an explanatory variable having an effect on a dependent variable. The null hypothesis says there is no effect, but we can test, and if our test is good enough, we reject the null hypothesis and say there is an effect. We didn't do an example like this, but the hypothesis can be any other kind of statement about the population parameter. It might not be a variable dependence. It might be just that the value of the population parameter is above or below some threshold. How did we test a hypothesis? So far we did it through simulation. If the null hypothesis is true, we can generate random samples. If we do this enough times, we get a sense of how likely our sample is. If our sample is very unlikely, then we have justification to reject the null hypothesis. Now, what are confidence intervals? Well, instead of a yes-no question, this is about a range of values. A confidence interval measures the size of the effect of an explanatory variable on a dependent variable, or the range for a population parameter. Instead of a yes-no, null alternative hypothesis question, we want to use our sample to say something about the range of values in the whole population. It's not about statistical significance anymore. That's a hypothesis term. It's about where we think the population might be using only our sample. How do we figure out a confidence interval? Like hypothesis testing, we use probability again. And again, we can do this mathematically with probability theory or by simulation. And we'll stick with simulation for now. Here's an example to try to explain what is going on with confidence intervals. There is a strange game you can play with two people, while one person taps out the rhythm of a well-known song, and the other tries to guess the song only by the rhythm. This turns out to be harder than most people think. A certain study did this with 120 pairs of people. Only 3 of the 120 pairs actually had someone guess the song. This is our sample statistic, a 2.5% success rate. The sample statistic here is just a single percentage, unlike the percentage difference in the previous video. This is all we have to go on. We have just this study. What is likely true about the general population? How often would someone actually guess the correct song? That's the population parameter. It's almost certainly not exactly 2.5%. That would be strange and uncanny. But we want to try and give a range what we think is reasonable for that population parameter. Using only this study, only this information, what range would we be confident in for the population parameter? Our study produces 2.5%. Maybe the range is 0 to 5. Maybe it's only 2 to 3. Maybe it's a larger range of 0 to 10. Where can we have confidence about the population parameter just based on our study? We're going to try a simulation to get at this information. How do we do this? The simulation method here is called bootstrapping and works this way. Very strangely, we assume that the sample statistic is the population parameter. But then, using that population parameter, we redraw samples of the same size as our sample. Then we calculate the probability of a range of values around our sample parameter using probability theory or simulation. It is an odd process, but it does produce a range around the sample parameter. Here's the graph for when I did our song guessing game. I assumed the population parameter was 2.5%. 2.5% of pairs would guess correctly. Then I asked a computer for random selections of 120 pairs from a very large population. I did this 1,000 times, and this is the histogram of those samples. From this, I made a confidence interval. Which confidence interval depends on the range of confidence? 95% is common, so I take the part of this histogram that includes 95% of the data. Such a range would be 0 to about 0.7. It excludes these 3 bars, which take up less than 5% of the data. If I look at the data more carefully, I could get a finer number than just 0.6 or 0.7, but this is enough for now. Using this probability simulation, 95% of the samples are between 0 and 6%. This is my 95% confidence interval. Other percentages could be taken. A 99% confidence interval would be 0 to 0.08. A 90% confidence would be about 0.1 to 0.5, and so on. Let me recap. The point is this. Knowing our sample, what can we say about the population parameter? We can't say exactly, but we can say a range. If our sample is without hidden bias or confounding factors, then it means that we can be 95% sure that the population parameter is between 0 and 6%. That's the point. Our sample gives us a range for the whole population.